All right, welcome back, folks. Cal 3, COVID-19 edition. Hope you're doing okay. All right, so 14.6, directional derivative and gradient. We've defined the directional derivative, and last time, the last thing we saw was a theorem that told us how we could actually compute the directional derivative pretty easily. So let me go back to that. I'll introduce the gradient at the same time, and then we'll finish with two very fundamental properties of the gradient vector and an application of this. Okay, so what did we see? So again, directional derivative, I have a function f, differentiable. We have a point in the domain of f, and we have a unit vector, which is the direction in which we want to take the derivative at the point x bar, right? And we saw the following result is that to compute the partial derivative of f in the direction of u at x bar, all we need to do is take the partial derivative of f with respect to x1 at x bar, multiply by u1, then do the same with respect to x2 times u2. And we keep on going, and we do this for every of the coordinate directions like that. Okay, and I did the proof in two variables, I think. Let me add somebody in. Yep. Good. And at the very end, I had you notice that if you look at this expression, then it turns out that it is a dot product, right? So notice that this is the dot product of two vectors. So this is, so I'll take the first vector, which is del f del x1 at x bar, del f del x2 at x bar, right up to del f del xn at x bar, dot u1 un like that, right? And so this is a very, very useful object, which is called the gradient of f at x bar. So let's define this. So the gradient of f at x bar, which is denoted, you might see grad f at x bar, or you might see this notation, which is the one that I'm going to be using. Okay, and what is this vector? It's precisely this vector. So you evaluate all the partial derivatives of f at the point you are interested in, x bar. Okay? Okay, so it's just a definition. We'll explore what it means a little later on. But just for the moment, notice this, that it's a vector in Rn. So this is a vector in Rn. F has n variables, right? So in a sense, it lives in the domain of the function, okay? So we can rephrase our theorem. Yes, I will wait a few seconds, okay? So we can rephrase the theorem as follows. Again, if I'm switching too quickly, just let me know. Okay, so again, the gradient vector at x bar, you just evaluate all the partial derivatives at x bar. We're assuming, obviously, f is nice enough so we can do this. We get a vector. And the relationship to the directional derivative is this. So if I want to compute the directional derivative of f at x bar in the direction of u, this is the gradient of f at x bar dot u. Okay? All right. So let's do a couple of actual examples. So let's say that f of xy is sine x plus e to the xy. I'm asked to find the gradient of f at a generic point xy and find the gradient of f at the point 0, 1. Okay? So nice and simple, right? So what is the gradient of f at a typical point? Well, so again, this is a function of two variables, so the gradient is a vector in R2, right? So it's del f, del x at the point xy, del f, del y at the point xy. So I just compute the partial derivatives. They're easy. Derivative of sine x with respect to x is cos x. Derivative of e to the xy with respect to x, this is y e to the xy. And then with respect to y, this is 0, and this is x to the xy. So this is the gradient in general at a generic point xy. So if I want this gradient at the point 0, 1, I'll just substitute. And so this is 1 plus 1 and 0. So this is the vector to 0. Okay. So it's a vector. I'm not telling you what it means for the moment. We'll see that in just a few minutes. But again, so the function f is a function of two variables. Its domain here is R2, right? So if I look at the domain, x, y, I look at the point 0, 1. That's the point I'm interested in. And so the vector, the gradient vector, if I locate it at the point, would be this. Gradient of f at 0, 1, and this is the point 0, 1 at that. So we'll see what it means in just a few minutes. Okay. Now, let's say I'm asked now to compute now, so find the directional derivative of this function of f at the same point in the direction of the vector v, which is 1, 1. Okay, so extra question here, directional derivative of this function at that same point, 0, 1, in the direction of v. And there you see the typical trap I told you about. You see that in a lot of engineering exams, calculus for engineers exam. You look at that vector v and you notice it's not a unit vector. So you have to be careful, okay? So let's copy this here. Okay, and let's just rewrite it over here. Okay. There we go. Okay, so I'm asked to find the directional derivative of f at that point, and I've got the gradient, so I know I can use that, but I have to be careful. The vector v is not a unit vector. Okay, so what do? You make it a unit vector. So you compute its length. So what's the length of V? It's the length of the vector 1, 1. That's square root of 1 squared plus 1 squared, the square root of 2. So now I find my unit vector in the same direction. It will be 1 over root 2 times V, which is 1 over root 2, 1, 1. Okay, so this will be the vector u I can use for my directional derivative. Okay, so del f del u at the point 0, 1. We've seen that to compute this, we need the gradient at that point, and you take the dot product with the vector u. I've got my gradient over there, it's 2, 0. Dot product with 1 over root 2, 1, 1. And of course, these constants that multiply vectors, you can just factor them out. So this is 2 times 1 plus 0 times 1. So this is 2 over root 2, or if you prefer, root 2. Same thing, right? Okay, so gradient, useful tool for the directional derivative. Straightforward to compute. And we're going to see some more uses of the gradient right now. Okay. All right. So directional derivative, straightforward, and we know we saw the meaning, the definition earlier. And so let's see some fundamental properties. So fundamental properties of the gradient. Number 1. Okay, so here's a very natural question. Okay, so this first property is actually very simple to figure out, okay? So here's the question. I give you a function f and some point in the domain of f. And the question is, in which direction is the rate of change of f maximum or minimum at x bar, right? So think of it this way. The way I like to think about it is, so if you have a function of 2 variables and you have a surface, which is the graph of your function f, okay? And let's say, I don't know, let's something like that. And you have your point x bar over here. So you're on the surface like that, and you'd like to know in which direction the surface, the rate of change on the surface is maximum or minimum, okay? So think of it this way. Suppose that you have a drop of water that falls on the surface. On the graph, and I ask you in which direction is it going to start moving due to gravity. Right? So that's basically the direction we're looking for, right? So this is where this the surface is steepest? In which direction is steepest? So in which right? Okay, so what does that mean? Okay, so let's find, actually, if you think just a few minutes about this, the direction where it'll be steepest going down should be opposite to the direction where it's steepest going up, right? So this sort of clear, okay? So let's just find the maximum, and the minimum will pop out the same. So we want del F, del, okay, sorry. We want to find U such that del F, del U at X bar is maximum. Okay, so that's what I'm looking for. Okay, so let's use what we found earlier to compute this partial derivative and see how we can figure out where it's maximum. Okay. Okay. So let's write it out. So del F, del U at X bar, what is that? That's the gradient vector at X bar dot U. Okay? Now, that's a dot product, so we have another way of writing it. We know this is the same as the magnitude of this first vector times the magnitude of the second vector times the cosine of the angle between the vectors. So the vectors are the gradient and U, right? Okay, we can simplify this certainly because the length of U is 1. It's a unit vector. So this is the length of the gradient vector at X times cos theta, right? And I want this, so when is this maximum? Well, the length of the gradient is positive or non-negative, right? So the way to make this as big as possible is to make the cosine as big as possible. So make cos theta as big as possible. What's the maximum value you can get for the cosine? It's 1, right? So this happens when cos theta is 1. Okay, when is the cosine of theta 1? That means theta is 0. So what does that mean? It means that the vector u and the gradient at that point, their angle should be 0. In other words, they should be pointing in the same direction. U is same direction as gradient of f. Right? So what did we find? We find an interpretation for the direction given by the gradient vector. It points in the direction where the rate of change is as big as possible. Okay? So a nice and simple interpretation of the gradient. Okay, now let's rewrite this. Okay, so I'm just going to rewrite what I had here. Okay, to see the value I get and to try to get the minimum also. Although, if you think about it, if you're pointing in the direction opposite to the maximum rate of change, you should have the rate of change which is negative, so it has to be the smallest you can get, right? So let's do that. So if u is in the direction of gradient of f at x bar, then theta is 0, and del f del u at x bar, if you go back to the previous slide, you'll see that this is the value you get, so it is maximum among all directions. Okay, so the direction of maximum increase is the direction of the gradient, and the value is the length of the gradient. Gives you that rate of change, which is pretty cool. Okay, so to get the minimum, you want the cosine, if you go back, so note, to get minimum, for allowing obvious minimum, by we mean, of course, largest negative, if such a thing, if there's such a thing in x bar. So to get the minimum rate of change, so opposite direction, that makes sense. Or if you want to do it directly, you can use this. So del f del u, again, is length of the gradient at x bar times the length of u, which is 1, times cos theta. This is minimum if cos theta is minimum. And this happens if it's -1. That's the least possible value you can get for the cosine. And how do you get an angle? Which angle will give you the cosine equals -1? It's pi. Right? So that means you're pointing in the direction opposite. So minimum appears opposite of gradient of f. Okay, so let's just recap this in the theorem. So I have f differentiable x bar in the domain of f, then del f del u at x bar is maximum in the direction of the gradient and has value length of the gradient. Okay, so as you can see, deriving this is pretty straightforward. Okay, so the gradient gives you, it points, if you locate it at x bar, it points in the direction where the slope is largest, where it's the hardest to climb, right? And opposite to that is easiest to go down. Right? Okay, so here is maybe a little example of this. And I'm going to spice up, if I can say that, the question, so we have to work a little bit more. Not that much, but okay. So here's an example. F is x e to the power y. We're asked to find the rate of change of f at the point P, which is 2, 0, in the direction from P to the point Q, which is 1/2, 2. Also find the max rate of change at P in this direction. Okay. All right. So we're given the direction from a point P to a point Q. What I want, obviously, is a unit vector pointing in that direction. I need unit vector in the direction from P to Q. Right, so what do? I look at the vector PQ first. What is that? I'll just subtract 1/2 2 minus 2 0. This is minus 3/2 2. So that's pointing in the right direction, but it's not a unit vector. So I'm going to compute its length. What's the length of PQ? Square root of 9/4 plus 4, which is square root of 9/4 plus 16/4, square root of 25/4. Ooh, look at that. Amazing coincidence. That's 5/2. Okay, so unit vector U will be 1/5/2 times PQ, which is minus 3/2 2, if you prefer, 2/5 times minus 3/2 2. So that's our unit vector U. Okay? So first I'm asked the rate of change of F at the point P in the direction given. So that's my direction vector U. To find the partial derivative, to find the directional derivative, I'll need the gradient at 2, 0. Okay, so I'll compute the gradient in general. Again, this is del F del X, del F del Y. I didn't bother writing the XY there. It's a generic point. So let's see, our function is x times e power y. So this is e power y, and this is x e power y. So that's our gradient in general. So the gradient at 2, 0, I'll just substitute. So e power 0 is 1, and this is 2. Okay, so I've got my gradient. Okay, so here, got a little junk here. So these are, these are my 2 ingredients. This is the vector U here. Okay, so I've got my gradient at 2, 0, and I've got the vector U. So del F del U at 2, 0. We know by theorem that this is the gradient of F at 2, 0 dot U. And so I just compute my dot product, 1, 2 dot 2/5 times the vector minus 3/2 2. We can always factor out the constant factors. So this is 1 times minus 3/2 plus 2 times 2. So that's 2/5 times 4 minus 3/2. 4 minus 3/2, that's 8 minus 3 5/2, that's 1. Okay? So this is the directional derivative in the given direction. Okay. The second part of the question was find maximum rate of change at the point in question at 2, 0, and direction of this. Okay, so we know it's given in direction of the gradient at that point, gradient of f at 2, 0, which is 1, 2. Now, you could, let's say you're doing a WebWorks, they might ask you, they might insist on a unit vector, but, or a unit vector in that direction. Right, if required. I'm not sure if there's a question like that in the WebWorks, okay? And the value we know is the length of this vector. So here's the length of the vector 1, 2, square root 1 squared plus 2 squared root 5. So this is the maximum value. If you compute the directional derivative of this function at this point in any direction, the maximum value you will get is root 5. That's the steepest direction. All right. So far, so good. Yeah. Okay. So that's our first fundamental property of the gradient. That's pretty straightforward. The second one is just a little bit trickier, but only slightly, just a little bit. Okay. Geometrically, if you think, I'll try to give you an intuition of it, and I think it makes sense, but to actually prove it requires just a little bit more finesse. Okay. So here's our second property. Okay, this is very useful. Okay, so here's the intuition that I'd like to give you. Okay, so let's say that we're looking at the graph of f, and think of it as a mountain. Okay, so let's just think of it as a mountain, something like that. Okay, and we have our base point, that's the x bar we keep talking about, and I look at what's happening on the surface at this point. So we've seen in our first property that the gradient, so the gradient here is a vector in the plane, and it points in the direction where the mountain is steepest to climb, right? So the gradient would be pointing in this particular example, something like this, right? So the slope is steepest going to the top of the mountain, so that's what the gradient, that's where the gradient is pointing. Now, suppose try to imagine yourself on a mountain, right? And you're standing here, the steepest direction is like this, right? That's the steepest going up, steepest going down, opposite. When would it be flat? So intuitively, hopefully you see that this would be perpendicular to this direction, right? So that's basically the intuition. Okay, so so steepest, up or down, direction of gradient. Right? And intuitively, the flattest part, if you're going to walk on this mountain and you don't want to go up or down, you're basically going to be walking perpendicular to that steepest direction. Mm-hmm. So, and the flattest direction perpendicular. Okay, so what are we saying? So what does it mean flattest? It means these are the level curves, basically, right? Okay, so what I'm saying basically, so if you let's look at this picture from the top. Let's look at the domain now. You're looking at your mountain. These are the level curves of your mountain like that. And you take a point on the mountain. The steepest direction will be perpendicular to the flat part. Right? So that's what we're aiming for. Hopefully this makes some kind of sense. If it doesn't, I will prove it. So you should be okay. So what we're aiming for is that the gradient at x bar is perpendicular to the level curve through x bar. So I'm talking about level curve here because I'm considering a function of two variables, but this will be true for any number of variables, and we'll see how we can use that, okay? So this is what we'd like to verify. Okay, so here is a first example where we can verify this, and hopefully we won't get lost in the algebra of the thing. Okay, it's a simple derivative, but I want to show you something that actually looks like a mountain and to try to convince you that we're getting the right thing. So let's see. Okay, so here's a simple example, two variables, just like I was illustrating. So let's take f of xy. Actually, no, I'm going to take a simpler example. It'll be a mountain upside down. So sorry, but it'll be simpler algebraically. Okay, so let's consider f of xy is x squared plus y squared. Okay, so what does the graph look like? The graph is the surface z equals x squared plus y squared. So this is this paraboloid, right? Circular paraboloid, okay? So let's look at the level curves of this. Okay, so a reminder, what are the level curves? Fix some value k, and you look at the set of all points in the domain such that f of xy is equal to k. So in our case, it'll be the set of all xy such that x squared plus y squared equals to k, right? So these are the shadows of the horizontal slices of our surface. So if you look at this from the top, well, as you can see, you're going to get concentric circles, right? Okay, so that's what it looks like. So these are the curves where the function is constant. Okay. So now I'd like to look at the gradient as compared to these curves. Okay, so let's look at the gradient. Okay, so the gradient of f at a generic point xy, what is that? Partial derivative with respect to x is 2x, partial derivative with respect to y is 2y. And I'll just write it this way, it's 2 times xy. Okay, so Notice this, okay? So observe. If I take the point xy as a point, and I view it as a vector, right? So I take xy over here, and I see it as a vector, I locate it at the origin, that's this vector xy, right? So the gradient of f is a multiple of this vector, so it's pointing in the same direction. So gradient of f at xy, the multiple of xy, so same direction, right? So that means that if you take any point xy like that, your gradient is pointing in the direction opposite the origin everywhere. I'm not considering the length of anything here, right? So you see that your gradient at all these points is perpendicular. Of course, it's a very simple example, but it's perpendicular to the level curves at every point, okay? So I just wanted to do a very simple computation so that you see what I'm talking about. But again, intuitively, this should make sense. Okay, now I'm going to do one in 3 variables. Yeah.
Sir?
Yep.
So this should be true to any kind of level surfaces, right? Not only.
Yes. No. Yeah. So depending on the function you have, you might have very complicated level curves. If you take the gradient at any point, it'll be perpendicular to that level curve.
All right. Thanks.
Okay. So let's do one in 3 variables. Although it's very, I'm gonna take one which is extremely similar. But again, you have to keep in mind the dimension here is so you have to take care of where these vectors live and what the level surfaces are. Okay, so let's take f of x, y, z is x squared plus, so this is just a higher dimensional analog of what we did, right? So this is my function. Give me just a sec. Okay. All right, so this function, the domain is R3, right? So I can't graph it, I need 4 dimensions. So what I'm going to look at are the level surfaces. Right? So again, what's a level surface? I fix some value of k, and I look at all the points such that the function has value k, where the function is constant. In this particular case, this will be where x squared plus y squared plus z squared equals this k. So these, as you can see, are concentric spheres. Right, so again, now I'm not looking at the graph of f, I can't see that. I'm looking at the domain of f. So in 2 dimensions is what we were looking at from the top. And so I'm looking at spheres like that. So when you look at the value of the function on these spheres, it's constant. It's always the same value, okay? Now I'm going to compute the gradient. At some generic point x, y, z, and it's easy. This is 2x, 2y, 2z, right? Partial derivative with respect to x, y, and z. And as we did in 2 variables, you see that this is the same direction as the vector x, y, z. So it points away from the origin. right? So if I take a point on this sphere here in the domain, I compute its gradient. The thing is pointing outwards. So I'm going to draw the tangent plane here. This is where we're going to go after. But so this thing is actually normal to the tangent plane for this surface. Okay, and this is true everywhere. Okay, so it turns out that gradient of f is perpendicular to the level surfaces. Okay, I would like to show you why this is true. Okay, so I've just given you examples, very simple examples. It illustrates, but it shouldn't be convincing. So why is this true? So there is one little thing that we have to figure out is what it means to be perpendicular to a surface. We haven't really, I mean, we have some intuition of what this is in the case of a sphere, but in general, what is it supposed to mean? Okay, so this is the only sort of tricky little thing, but if I'm just going to do it separately, and I think I can convince you that it makes a lot of sense. Okay, so let's do that. So technicality, yeah. So what does it mean to be perpendicular to a surface? And the nice thing about this is that it works for any dimension, but I'm going to stick to 3 dimensions. For 2 dimensions, if the function has 2 variables, this should work out because you're going to, so let me just note, perpendicular to a curve, right? This should make sense. So if you have a curve like that, and you have a point like that, what would it mean to be perpendicular to the curve at that point? Well, you think perpendicular to the tangent, right? So that's the natural, thing, means perpendicular to tangent, right? So that's okay. But when we go to a surface, we haven't really discussed this before, so how do we do it? Well, the trick is do the same thing that you do in 2 dimensions. So for 3 dimensions, what you do is this. And it's a nice trick. So I have a surface, I have a point, and I'd like to define what it means to be perpendicular to the surface at this point. So if you think about it, so take any curve that passes through this point like this. Take any curve like that, all these curves, right? Now, intuitively, if you're perpendicular to the surface, you should be perpendicular to any of these curves. And this, we know what it means. It means you're perpendicular to the tangent to any of these curves. So it means, so that's how we're going to do it, means, sorry. So vector, let's say, W is perpendicular to S at X bar means perpendicular to every curve in S at X bar. Yeah, I should say to X bar at X bar, right? So if you take the tangent to any single curve, which is in S, the curve has to be through S. You look at the tangent vectors there, then this vector W should be perpendicular to all of them. So W perpendicular to tangent vector to all curves in S at X bar. Okay, so this is the way we're going to define perpendicular. Okay, so then we should be able to handle this. Okay, all right, so how are we going to do it? So let me state the theorem. So it's sort of a mouthful, but I think up to this point, I think we should be okay. So so here's the result now. Okay. So here, and this is the property we're after. I have a function f. I'm going to state the result in arbitrary dimensions. If just think n equals to 3 or 2, it's fine, okay? But I don't want to repeat it for 2 or 3. I want to do it one shot. But I'm going to do the proof only in 3 dimensions, okay? So I have f defined on some domain, which is a subset of Rn, okay? It has continuous partial derivative, so it's nice. Let me write it, but okay. X is my point in D, okay? And I'm going to call the value of f at this point, I'll call it k. Why do I need this? I need because I want the level surface which contains x, okay? Okay. We're going to make an extra assumption. I mean, this theorem is like really a bit heavy to state, but you have the intuition and the proof is actually not too difficult, okay? So assume that the gradient of f at this point is not the 0 vector. Otherwise, this is not interesting, okay? Okay. Then what we're going to say is that the gradient of f at this point is orthogonal, perpendicular, orthogonal to the level, I'll call it a surface, to the level surface, the set of all surface containing x bar. Okay. So what's this level surface? I'll write it up right now. Okay. So by orthogonal, again, that was my technicality. I mean that it's orthogonal to any curve in that level surface through x bar. Okay. I'm almost done. Okay. So stating the thing is harder than actually figuring out why it's true. Okay. So here's the proof for n equals to 3 only. Okay. Okay, so S, my level surface, is the set of all x, y, z such that f of x, y, z is equal to what? Is equal to k. So that's the value of my function f at my interesting point, right? So x bar is an S. That, I'll just draw it like this. X bar is here. Okay, I want to show that the gradient of f at x bar is perpendicular to S, and as I said, that means it's perpendicular to any curve in S through x bar. Okay? So I'm going to take a curve, okay? Sorry, if I seem distracted, is because there are people in the house who have forgotten I'm actually teaching right now, and I don't know what they're doing, but sorry, it's on the record now. Okay, so I'm going to take a curve, going back to early Cal 3, from some interval I that goes into R3, so it's a space curve, okay? What do I need from this curve? I need that it passes through the point x bar. So now there would be a point in the interval, some time, where r at that time gives you x bar. Let's just assume that it is 0, okay? So where r of 0 equals to x bar. So assume that 0 is in your interval, your time interval. You just can just change the values of your interval. It makes no difference, okay? And what else do I need? I need this curve to be in S. So we need image of R is in S. What does that mean? It means that R of T is in S for all T, which means what? Just give me 1 sec. Sorry about that. Okay, so let's try to finish this up. Okay, so what does it mean for R of T to be in S? That means, so what is S? It's all the points where F has value K. So that means F of R of T. So if you evaluate F on any point of this curve, you get K over N T. Okay, so let me do a picture again. This is S, X bar, your curve, R, passes through the point here. Okay, so it's in S. And I want to show, what do I want to show? I want to show that the gradient of F at X bar is perpendicular to R at X bar. What does that mean? It means that the gradient of F at X bar should be perpendicular. So R at X bar, this is R of 0. You take the derivative there, that's the tangent, right, to R prime of 0. In other words, I want to show that the gradient dot R prime of 0 is 0. So that's what we want. Okay? This is a bit heavy, I know, but it's not so bad. If you reread it slowly, you should be fine. Okay, so we're basically there. So if you remember what we did in 14.5, we did one thing that we've been using all the time since then. It's the chain rule. Yes. So that will pop out of the chain rule almost immediately. So this comes from the chain rule. Okay, so let's just do that. 1 minute and I'm done. Okay, so what do I have? So let's just write this. Let's just call R of T, let's call it X of T, Y of T, Z of T, right? And the key point is what we've got here. When you apply F to R at any T, you get a constant value K. So F of X of T, Y of T, Z of T is K for any T. right? So you apply the chain rule to get the derivative of the composition with respect to t, right? And what does that tell you? What does the chain rule tell you? So you take the derivative both sides. Okay, so on the left-hand side, what's the chain rule? It'll say it's del f del x dx dt. I'm not evaluating it, so it'll be more concise this way. Del f del y dy dt plus del f del z dz dt. So that's the left-hand side. What is the right-hand side? It's the constant function k, so it's 0, right? So that's what we get. And basically we're done, right? Because if you look at what we have here, if you evaluate it properly at t equals to 0, you get exactly this, okay? So let's just copy this. Okay. So this is what I got. So evaluate at t equals to 0, and then we know that f evaluated, so the partial derivatives will be evaluated at x bar. Right? So we get, so this is just the dot product. This is basically del f del x at x bar, del f del y at x bar, del f del z at x bar, dot dx dt at t equals to 0, dy dt at t equals to 0. I'm going to run out of room. Maybe not. Okay. I rewrote the left-hand side as a dot product. Okay, it's cleaner. And what is that? For the left-hand side, this is the gradient of f at x bar dot, what is that? That is precisely the derivative of r at 0. Right? So that means this. If you have r like this is r of 0. This is r prime of 0. It's the tangent vector there, and the gradient must be perpendicular at this point. Okay, so this is like on the heavy side, I know. Okay, remember the intuition. Remember there's the chain rule, which is used to get to this, right? I'll stop here, and next time I will refresh your memory about this and see how we can use that to compute tangent planes to surfaces. Any questions? No questions? All right, so as usual, I'll post the video and I'll post the slides, and hopefully that wasn't too bad. All right, so I'll see you next time. Cheers.